Hi, my name's Rohan, and today I'll be interviewing Professor Milenkovic from UW Madison. So let's get right into it, and can you tell me about what your parents did?
Well, first introduce myself. My name is Paul Milenkovic. The family name Milenko is a variant of Michael, Mikhail, Milenko, and the Vic at the end is a patronymic, meaning son of. So Milenkovic is how I and my relatives pronounce the name in the English language. I was discussing with, call me Paul, I was discussing with Rohan um, influences on my career at the UW Madison. I started here in 1982. So that means I've been here 42 years as a faculty member in the Department of Electrical and Computer Engineering. I mentioned that my parents were an important influence on my career and the kind of work that I'm doing. I'm currently engaged in research in related to robots and robot motion planning. My father was doing this kind of work at the time he retired in 1987 from Ford Motor Company. A little bit about my parents is that my father, Veljko Milenkovic, uh, was born in Zagreb, Croatia. It was then part of uh, the Kingdom of Yugoslavia, which after World War II became, I believe, a socialist republic under the leadership of Josip Broz Tito. Um, my mother was born in a province of Serbia, then part of the Kingdom of Yugoslavia. The province is called Vojvodina, which is multicultural, multi-ethnic. That province includes speakers of German, Serbian, or the Serbo-Croatian language, and Hungarian. My mother was raised as a native speaker of the German language, though she learned the Serbian language to attend school. Both of my parents were refugee immigrants that they were displaced from their homeland in the course of the events of World War II and made their way to the United States, that they were sponsored by church or other non-governmental nonprofit organizations who facilitated their immigration to the United States. They relocated to Chicago, and that's where my parents met each other and then married and started their family. And I'm the middle of three of their children. That maybe saying a little bit about my mother is that my mother was, I say this in the past tense, is that they have both passed from this life in their old age. Though I thought my mother passed relatively young, is that she had a progressive neurological disease, which left her immobilized towards the end of her life. That my mother takes credit that my father continued his engineering education here in the United States, which he had started as a refugee immigrant in Bavaria in southern Germany, and completed a bachelor's, master's, and Ph.D. degree at Illinois Institute of Technology. At the same time, working and supporting the family. My mother's education, besides rigorous education through high school, which was the standard for both their station life in Yugoslavia, my mother had, I don't know what the equivalent would be in the United States, training in dress, clothing construction and design. She worked at that until she retired from that job to be a homemaker full time. So my mother was a very important motivation, that encouraging my father on basis of principle, that my mother felt that he had the intellectual capability to do this, and it would be a waste not to continue to his PhD. I have a doctorate in the sciences, as do my other two siblings, which was very much encouraged by my mother. Besides being a homemaker, my mother had a career as a political activist. There's two locations in the United States which are on my bucket list. One of them is the Clavey Road sewage treatment plant in Highland Park in southern Lake County, Illinois, near Chicago. The other is the department, well, I don't know what the arrangement is under the auspices of the Department of Transportation. There is a facility in Pueblo, Colorado. I believe it's a private contractor, which is under contract with the Department of Transportation, which is the railroad test facility. So they work with all kinds of trains, freight or passenger train, but any new passenger train design or passenger car or locomotive which is put into service in the United States is thoroughly tested at the Pueblo facility. So I suppose I could just contact the people at the sewage treatment plant and arrange a tour and tell them who I am and who my mom was. Well, in the 1970s, my mother was a political activist working, she was a member of the Women's League of Voters, and the political activism was on saving Lake Michigan and the other Great Lakes. And the avenue to doing that was to lobby for the upgrade of the sewage plant facilities so that to reduce the amount of untreated or partially treated wastewater going into Lake Michigan. I don't know if you heard about Lake Erie in the 1970s was a great concern that it was going to become dead. That is the result of the sewage or other pollution discharges into Lake Erie would mean that it would eventually turn into a swamp. Well, I don't know the current state of Lake Erie, but Lake Michigan, I think, is in pretty good shape, largely because the efforts of my mother and her political activist colleagues. And I looked this up online. Well, first of all, in terms of my mother's a political activist, I got to tour every sewage treatment facility in the greater Chicago area. And my sister jokingly referred to this as we became connoisseurs. It's like a pun, sewers, sewage treatment. And so I learned about the difference between primary, secondary, and tertiary treatment. And if somebody's interested, I have been told that City of Madison uses an advanced tertiary treatment, which is the highest level of treatment of the discharged wastewater. And they use that at Clavey Road because they're discharging directly into Lake Michigan. Cook County, which is Chicago and the inner ring of suburbs, famously discharges into the Mississippi River watershed and doesn't discharge wastewater into Lake Michigan. And at least back in the day, they were doing secondary treatment, but the Clavey Road facility was using the tertiary treatment. And my mother got involved in a political controversy. You heard of NIMBYs, not in my backyard, of residents who didn't want the expansion of this tertiary sewage treatment facility to accommodate the growth in population. So there were people who are very unhappy with my mother's political activism. And my mother took it personally, but okay, what is they did expand the Clavey Road facility. And years later, I think after the passing of my mother, I looked it up. this facility won an award for the quality of their operation. Now, what's so hard about, what I learned with my mother's political activism, and my mother was involved in the technical details of the different types of sewage treatment plants, was informed of what it would take to preserve Lake Michigan and the other Great Lakes. And that influenced my education. So my mother wasn't just, oh, we're just in favor of stopping pollution, is that she was very studied on what the technologies were and what was involved in properly treating the wastewater and what the engineering trade-offs were. And so I'm imagining that you can't just turn some valves, is that you have to be conscientious. The secondary treatment phase involves what's called active sludge, a bacterial culture, which reduces precipitates out more of the organic matter in the wastewater stream. And so if Clavey Road won an award, they must have been very conscientious and had good procedures and be very dedicated to what they do. And I credit my mother in part for helping make that possible. But my mother's involvement in that was an inspiration to my career as an engineer, but also somebody from childhood who was interested in protecting the environment. That you want to protect the environment, but you want to understand the engineering issues to make this possible. So the other bucket list item is this Pueblo, Colorado facility, which might be hard to swing because it's not a facility which gives tours to the public. They keep it off. It's not like there's some deep state secrets about high-speed railroad trains or improved railroad locomotives, but many companies test their prototypes there. And one of the things I learned working here at the university and following in my father's footsteps, working in robotics, I have 4 patents on this, on robotics technology. And there's this idea that you don't want to make public disclosures until you've filed your patent. And by keeping this a closed facility, they meaning either the government or private companies, let's say Bombardier supplying equipment to Amtrak for the Acela train, they can test the equipment there before they filed all their patents, because operating in that facility does not count as a public disclosure, or at least that's my understanding of it. But anyway, that's on my bucket list. I would like to go to that facility. Now, why do I want to go to that facility? Part of my father's career as a research engineer is he worked for a company called GATX, General American Transportation. And the X means that they own railroad cars, and they don't own a railroad. They don't own any tracks. You may have seen GATX stamped on. Rowan, you're in the Milwaukee. No, you're in the Sun Prairie area.
Yeah.
If you've visited Madison, there's this train which runs through the campus of UW Madison, and you may have seen there or other places tank cars which say GATX on it. It stands for General American Transportation, and the X means that they are a non-railroad leaser of railroad tank cars and other types of railroad cars. So they had a division. Now, I don't know how much of this is still extant because of corporate reorganizations and all of this. It was called GAR, General American Research Division, which started out as a laboratory affiliated with my father's alma mater in the United States, the Illinois Institute of Technology, which is on the south side of Chicago, near where Barack Obama began his political career. And this lab was then spun off and sold. It may have been sold to AMF, American Machine and Foundry. And my father's connection to AMF is how he attributed to a pioneering robot design, the Versatran robot. But at General American Research Division, there was a government contract to build a test stand for the Pueblo facility. And the idea was we were inspired by the Japanese Shinkansen, which we call the bullet train because of the streamlined high-speed electric trains, which the Japanese put into service in the mid-1960s. And the Department of Transportation was funding research into what it would take to have a similar kind of train. And the idea was to build a test stand to instead, this Pueblo facility actually has a loop of track where they can operate trains on. But if you have something stationary and you have shakers, and the original idea is you'd have these ribbons of steel simulating the rails. They simplified it to using rollers, which are not quite duplicating the conditions of actual railroad operation. So it's the roller test stand. And the roller test stand, the rollers were on shakers, which moved in multiple axes, because the idea was to simulate bumpy tracks or maybe smooth tracks, but the bumpiness of trains approaching hundreds of miles an hour. So what you needed, you had a dynamometer, which was, if it was a locomotive supplying power, that it would be a generator which would absorb that power, or if it was a trailer railroad car, it would be a motor which would motor the rollers to put the wheels in motion of this train car on the test stand. So my father's contribution to this was the mechanical power coupling from the stationary the stationary dynamometer slash motor generator to the roller on connected to a shaker where you put the vehicle on. And my father talked about the government. Okay, we complain about the federal government, but there's many things that we as a society do together with our federal government. So what the specification was, 300 miles an hour. The Japanese were operating trains at 150 miles an hour. Now, it was to look forward to the maximum possible speed that we'd run a railroad train. Then it was a 50-ton axle loading. I think currently the axle loading limit is 35. Maybe it's being increased to 40 tons, and that's for slower moving freight trains. Certainly for a purpose-built high-speed rail like the Japanese one or the California high-speed rail under construction, you're not going to have a 50-ton, let alone 40 or 35-ton per axle loading. You'd have a lighter weight train than that, and you'd restrict the high-speed rail line, as the Japanese did and as the state of California is planning, to passenger trains, and you wouldn't put heavy freight traffic on it. So it's 300 miles an hour, and it was 50-ton axle loading, and then it was some very large factor of adhesion. Now, actually, with electronic wheel slip controls, the TGV, the French high-speed train, as well as the German, the European high-speed trains, use locomotives to tow trailer cars. They get very high factors of adhesion because they have electronic wheel slip control, which was not anticipated that this would be achieved in the 1960s. And so they assumed 50-ton axle loading, 300 miles an hour, some very high factor of adhesion that my father thought was only realistic under slow speed conditions. And it came up with this ridiculous horsepower specification. So the thing was way overspecified. So it was a real engineering thing to build this power coupling. And what was this power coupling? It was essentially a scaled up version of the CV joint half axle in your front wheel drive car. Your front wheel drive car has to transmit, reason it needs a CV joint, constant velocity joint, is when you turn the wheels, you don't want the effect of a universal joint, which is not constant velocity, which would cause a varying speed of the wheel, or if the wheel was going at constant speed, it would cause a vibration in your drivetrain and would wreck your transmission. So your front wheel drive car has four constant velocity joints. You have a pair of constant velocity joints and a spline joint connecting them. So essentially, it's called a half axle. And if you've owned a front wheel drive car long enough, you may have had to go to either the dealer or a specialty shop that used to be one in East Washington to replace them at some considerable expense. Well, this was the biggest multi 10,000 horsepower or some huge horsepower to meet that federal specification half axle. And my father came up with a novel constant velocity joint design, which would transmit the torque and the horsepower they had in mind. And he published a paper on the design in ASME, American Society of Mechanical Engineering Journal. And I remember Mom, women in our culture, but maybe in many cultures, are fiercely protective of their husbands. And so this had an open review. There were two reviewers who made review comments, and then my father responded to. Usually, when you submit a scholarly article, it's sent out for reviews, either accept the revision or reject. And if it's accept the revision, the author or authors read that, make the changes, and go through some revision cycles. And the associate editor, the person supervising the review, is listed on the published paper, but the reviewers. But here, the reviewers were listed. And so, my mom said, oh, those terrible reviewers and the nasty thing they're saying about father's power coupling. Well, who the two reviewers were Kenneth Hunt from Australia, who was from his publication record, the authority on constant velocity joints in terms of the mathematical or geometric theory behind them. And the other one was Ferdinand Freudenstein, this Austrian emigre, who it was essentially the godfather of everybody working in the type of work I'm doing on robotics, the kinematics, which is essentially the motion design of the robotic mechanism. And so they got like the two highest ranking people in the field to review my father's paper, which was published. But the interesting thing was that Kenneth Hunt, who had this universal theory of constant velocity couplings, was nonplussed because my father's coupling wasn't encompassed by an obvious extension of Hunt's theory. It wasn't one of the cases that Kenneth Hunt had envisioned. So that's also my father's connection to robotics research, because after working in General American Research Division, he was recruited by Harry Johnson at Ford Motor Company, who was somebody he had worked for at AMF on the Versatran robot in the early 1960s. And in my father's career at Ford Motor Company, he developed a so-called singularity-free wrist, which is robot singularities. And singularity-free wrists is part of my research since 2009 or 2006, that time frame here at the university. And it turns out that robotic wrist works on similar geometric principles to a constant velocity coupling in terms of how it achieves its wide range of mobility. So all these things are connected. And so I mention this in terms of my mother was the motivator in the family, both of her husband as well as her children, to pursue what we now call STEM, science, technology, engineering, and mathematics careers. And And uh, my mother was also an inspiration with regard to technology, her combining science with environmental activism. And then, of course, I always found what my father was doing, whether it was the research in support of high-speed ground transportation, what they called it at the time, and later on, earlier in his career, his work on robotics, and then he returned in his career to work in robotics, has been an inspiration. And much of what I've been doing at the university since 2009 is essentially taking it up where my father left off on robot singularities, where robots have special alignments of mechanisms where the mechanisms lose degrees of freedom, which confounds their programming in an industrial environment. So I'll come up for air at this point. If you have some questions that I elaborate on some aspects of this.
I don't have any big questions yet, but I just want to clarify, like around what years was your mom doing this activism?
Where?
Or like what years?
That was in the 1970s. And now my father spent 10 years at Ford Motor Company, essentially leaving the Chicago area in 1977. He was invited to join Ford and work on robotics by Harry Johnson, who was somebody that he worked with and Harry was his supervisor at AMF on the development of the Versatran robot. And so I think maybe 1973 through 77. So when my mother left the Chicago area, that she was active in some activities outside the home, but the environmental activism was specific to the Chicago area in terms of protecting Lake Michigan by advocating for upgrades or constructions of high grade sewage treatment facilities.
I don't have any other questions then so far.
Okay. If you're okay with this sort of eclectic approach, and I pointed out how the high-speed ground transportation is tied into the robotics research, in the sense that one of the culminating patent of my father's career is something called a non-singular wrist. And that if you have a universal joint style pointing device, that is, you have a deflection in, I should know the technical terms. Let's say you have a forearm rotation, and then you have a wrist deflection. That's 2 degrees of freedom. That when the axis direction of the forearm is lined up with your finger twisting direction, you have something called gimbal lock, is that you can deflect the wrist this way, but you can't, a robotic wrist doesn't have the ability to turn the wrist in the second direction the human wrist is able to do. So when the robot forearm is lined up with the third robot joint, you're at a wrist singularity, which is also called gimbal lock. And my father's non-singular wrist, which was, he regarded this as the culmination of his work at Ford Motor Company, was essentially 2 such wrists put in series. And then there were 2 more wrists put in series, which surrounded the wrist in a shell. And this nesting of such wrists was very much the same thing that my father's constant velocity joint did. The reason you want to nest constant velocity joints is it reduces the vibration, is that you have two of these CV, constant velocity joints, 90 degrees apart. And so as you deflect the input and output shafts, you introduce some rotational imbalance on the inner one, which is countered by a rotational imbalance 90 degrees offset of the outer one. So the culmination of my father's career at Ford Motor Company was a patent on a non-singular wrist. My father pointed out it was singular, that were you to point it back 180 degrees on itself, which you could, because this wrist, the physical wrist they constructed could only point back 110 degrees, not the full 180 degrees. But over the plus or minus 110 degree working space, it did not have this this singular condition, which complicates the robot technician setting up the robot in the factory to do a factory task, especially in continuous motion tasks such as spray painting. So this idea of non-singular wrist became kind of a Serbian ethnic thing, because my father developed one, and somebody that he knew through the immigrant Serbian community, a man by the name of Michael Stanisic, who was a professor at Notre Dame, and unfortunately, I guess a year ago, he passed on suddenly, unexpectedly. It was never disclosed what he had. But anyway, he died suddenly, I think at age 64 or age 65, in that, not that old. That Mike had developed a non-singular wrist, but his was not an offset wrist. The wrist articulated on a common center, which simplified something called the inverse kinematic transformation, calculating from what the robot does to what the robot joint angles have to be. So, there was sort of a sense of kind of professional rivalry. I had seen, and Mike let me play with his non-singular wrist. And he said, "Oh, your father's non-singular wrist was quite the inspiration to the work I did." Well, I couldn't leave this alone. I had to invent, and Worf has been assigned the patent. I had to invent my own non-singular wrist, which, like Mike's wrist, it's spherical. It doesn't have the offset of my father's wrist. That it's not over-constrained, which my father's wrist design required precision manufacturing because it had redundant mechanical paths which had to exactly flex in the same way. And unlike Mike's wrist, which was limited to below a hemisphere, 90-degree deflection, mine, I don't know if I claimed 110 degrees or 105 degrees. I think maybe I claimed 100 degrees of deflection or something. And I built a prototype for it out of wood to just demonstrate. And I published a paper, and there's also a patent on it. And so I think that this wrist was an impediment to Mike talking to me, because his father knew my father through the immigrant community, and I met Mike at one of these robotics conferences that I accompanied my father to, which were held in Europe. And so one of my big disappointments is that in addition, these non-singular wrists, there's mine, there's Mike's, there's Dad's, there are other inventors who have such wrists. I don't see any of the robot manufacturers using them. In fact, the usual kind of robot wrist, which is sold for a painting robot, which needs continuous motions without interruptions, otherwise you spoil the paint finish. I have a wrist singular smack dab in the middle of the working space. So the alternative to that approach is to I do what's called singularity avoidance. And I have a series of publications, research publications, scholarly publications on this topic, which build on my father's patent on a singularity avoidance, where you steer the robot uh, away from the singularity. So you tolerate a small deviation in the pointing angle of the robot tool, but you compensate that the tip of the robot, where it contacts the work, or where the spray gun goes, or where the welding torch makes a welding seam, maintains a precise position. Uh, so that is extension of my father's work. And I'm finding that's also a hard selling industry. I guess they're kind of happy with the robot technicians jogging the robot and kind of futzing around rather than having an automatic way of doing this. But anyway, this is what I've been working on since the 2009 timeframe. But anyway, one of my criticisms of father, well, he worked with a colleague, with two colleagues, Bernie Huang and Ming Lu, who were actually PhD graduates out of the robotics program out of Carnegie Mellon University, which was a prominent place for this work to take place. That in their papers and patents, they talk about detecting the presence of the singularity, that as you get close to the singularity, suddenly the wrist joints start speeding up in order to keep track of the motion you're trying to produce. And no offense to my father, but I always thought that that was an engineering hack that needed to be improved upon. Well, Mike had a paper with a student, that's what we're expected to do as faculty members, is publish with students getting degrees, where he calculated something called the Jacobian matrix, which is the matrix of sensitivities of changes in the hand positions to small changes in the joint angles. And that he proposed the determinant. If you've been in college algebra or even high school algebra, that is something you calculate to solve a linear system of equations from a matrix. That doing this algebraic calculation gave you a prediction of approaching the singularity well in advance of reaching it. And I thought this was a huge contribution on Mike's part. And there was a PhD student, Aravind Bhaskar, who gave a talk in the Department of Mathematics a couple of years ago. And so I said, oh, I know Mike, say hello on my behalf. And I wrote my name. Paul Milenkovic says hello to Mike Sonishich on the blackboard. And I wanted to tell him about this work that I was doing. My most recent publication builds on his result. And a lot of scholarship is done that way. It's not like, oh, I was the first person to think about it. I wanted to tell Mike, your idea of this particular calculation of the distance from the singularity in order to anticipate the singularity and steer around it is an enabling technology of my most recent paper. And I wanted to share this with him. In fact, I was angling that he would invite me to Notre Dame to give a talk about it, because part of what we're supposed to do, besides publish papers and teach students and bring in money, is disseminate technology by talking to our peers at other universities. Never heard from Mike. And then I heard that he passed on unexpectedly. And it's sort of like, would have, could have. And I wanted to tell Mike about how underappreciated his work. I mean, a lot of his contribution was serving on, as a faculty member, you're expected to have an army of graduate students and publish half a dozen papers a year and bring in tons of money. And I'm not doing that, and he's not doing that. And I wanted to say, you're really making a very important theoretical contribution to the field, which in my recent paper, which was indispensable to move my recent paper forward. And I never got that chance. And I don't know if there was an element of jealousy, like, Paul wasn't even trained in robotics, and here he's publishing in our field and upstaging me or something. But I wanted to tell him, your work is really significant and it's significant to my paper. Invite me to Notre Dame to give a talk and buy me a dinner. I guess that never happened and will never happen. So that's that phase. I interrupt, you're interviewing. Courses are not an interruption. But, a faculty member, boy, we know how to talk. So the one thing that I want to talk about is my father's contribution to the Versatran robot. I told you about my mom being fiercely protective of dad in connection with two of the luminaries in the field of kinematics, which is the study of motion of machine mechanisms, were the reviewers on his paper on the constant velocity coupling, which was enabling of this roller test stand in the Department of Transportation facility in Boulder, Colorado. Your mother is very much like, let's say there were two robots. There was Joseph Engelberger, who developed the Unimate robot out in Connecticut. And there's my father, who contributed key ideas to the Versatran robot developed by AMF, American Machine Foundry, in the Chicago area. And people regard Joseph Engelberger and the Unimation as, the father of robotics and all this. But the Versatran was a rival, and the Versatran worked on an entirely different principle. The Unimate worked on a digital control where you move the robot to you had some joystick and you steered it to a point, and then you steered it to the next point, and then the playback read those digital coordinates, translated into joint angles, and it moved the robot on the pre-planned trajectory. That the Versatran robot, and by the way, Versatran wasn't just a clever marketing name. The idea was robot, even in the early 1960s or late 50s, when this was under development, was regarded as threatening in terms of, now people are worried that AI is going to take everybody's job. The idea is that robots are going to take workers' jobs away. The Versatran didn't have robot in the name. It was like the versatile transfer device, or at least that's a plausible story about Versatran. So Versatran used analog magnetic tape as opposed to a digital, it may have been a drum memory. I should get my facts straight on this, on the animation. But the digital technique is what all robots have been doing. The Versatran technique of the magnetic tape control has largely been abandoned. And what it was is that it was a pulse position modulation of a pulse position encoding of the rotation of the motor actuator through a gear reduction of the robot joint. Now, how this worked is that there is a timing pulse and then there is a signal pulse. And the timing pulses, let's say, for sake of argument, repeat every 1 second. If the signal pulse varies anytime between 0 and 1 seconds in that time frame between a timing pulse and the next timing pulse, that represents a certain measure of how far the robot joint is rotated. Now, what the key to this is that this analog technology using magnetic tape is notorious for not being very precise. That's why everything is going digital. But the idea was that you only measured a distance from the current timing pulse to the signal pulse, and when the signal pulse delayed, it fell into the next timing pulse frame. That's called a phase wrapping. And what the phase unwrapping was, the Versatran control system kept track of how many, so each uh, variation between 0 and 1 second, I'm using that as an example, it's a much tighter time interval, was one shaft rotation of the motor, which through a gear reduction operated the joint. And so this analog system tracked the um, the robot joint angle through maybe hundreds of shaft rotations. And by that way, with an analog technology, it obtained a very high precision. But not only that, because the magnetic tape, the analog magnetic tape stored much more information than a 1960s era computer that you could afford to connect to a robot, it allowed for continuous motion control instead of jerky robotic motion control. And part of what Father was doing, what Velko was doing at Ford Motor Company in the twilight of his career, with where computer memory became less expensive, you could have many more points, but there was a question, how do you interpolate between those points to generate smooth motions? And the work I've been doing at the University of Wisconsin is continuing where my father left off in 1987 with his retirement. I took this up in, oh gee, it took too long to take it up until my father ended up in his old age in long-term care for a failing memory. So I took this up in 2006, but not after, but this is after I had accompanied him, was co-author on some of his papers in retirement on robot motion control, which he presented in the former Yugoslavia. So let's check in here if you have some questions or if there's some things I can follow up on.
As right now, do you also want to spend a little bit talking about what else you're doing currently at the university?
Well, the bulk of my career at the university has been in speech signal processing, as well as the acoustic analysis of speech and something called the inverse articulatory to acoustic transformation, which is an extension of my dissertation research under direction of John Pierce at Caltech, which is where I did my Ph.D. degree. And the foray into robotics, yeah, it was partly motivated as being the family business. You know how some of the star race car drivers, their fathers were star race car drivers. And that as my father became infirm, it was kind of like, well, I don't want all this stuff that he developed in his career to just sort of, vanish. I was working on continuing this work and publishing scholarly articles on extensions of it. Now, is there a connection between the two? Like, did I launch into something completely different? Well, part of, if you're spending 42 years at the university, it's kind of rare that you're working on your dissertation research area. Many of my colleagues have moved into related areas or come up with some new ideas in order to find new sets of problems to take a fresh perspective on. Part of the connection is that in speech research, I was interested in modeling the relationship between the physical vocal tract, the position of the jaw, tongue, and lips. I was affiliated with the X-ray microbeam project here at the University of Wisconsin, where we had a custom-built high-voltage X-ray machine with very low dose of X-rays to track gold markers fixed with general glue to a human subject's tongue, jaw, and lips in order to track speech movement and make connections to the acoustic output. And I was working on constructing representative models, geometric models of the vocal tract, and then doing the calculation of what the resulting sound wave patterns were to relate the displacement of articulators of the human vocal tract into shifts in the speech spectrogram, which have a perceptual importance in speech. So one of the motivations moving into robotics was the family business. Another motivation was that I was working on the geometry of the vocal tract, and in fact, I had in my father's retirement starting in 1987. In the 1990s, I had involved him on conference proceedings papers that I had published on geometric models of the human vocal tract. And so that's part of where that connection was. Another connection, sometimes one of the advantages of the university, though, there are restrictions on what we do, is that we have to work with, we don't have to, but we're very strongly encouraged to work with students and bring in outside funding to support students. But sometimes you have an idea and you're just interested in it, and you have the academic freedom at the university to pursue this. Is that I thought that my father's mathematical proof of his non-singular wrist relied very heavily on encyclopedic knowledge of trigonometric identities. Like the cosine half angle and the twice, and the tan half angle is something in terms of sines and cosines and all this. And I thought that there had to be an easier way to understand robotic mechanisms. And you can stop me if I'm getting too overtly technical for the audience.
This is fine.
Podcast. There's two aspects which drew connections to my experiences as a research engineer and a professor in electrical engineering. One of them is a circuit is a linear device. Like when you learn circuits, the resistor, capacitor, and inductor, those use linear mathematics. The electronic devices, such as when you add transistors or operational amplifiers to the mix, are nonlinear. And that the way you solve electronic circuits, which is the next part of the undergraduate curriculum beyond circuits, is that you have an operating point, is that by whatever means, it could be trial and error, which I found when I was studying this. I thought, what's all this? By whatever means, you determine an operating point. Sometimes it's done by drawing a nonlinear diode curve and then drawing a resistor load line where they intersect is your operating point. And a junction transistor is actually comprised of a diode, actually a pair of diodes in its mathematical model. So using some graphical or other technique, you determine an operating point. And then about the operating point, you do a linearization, and that's called the small signal model. And there is something called the small signal model for robotic mechanisms, and it's called the screw theory. And the way this works is that a revolute joint, in other words, a rotating joint in a robot, can be described as a axis direction along with an offset of that axis, of a point along the axis line from the origin. And you come up with these 6 numbers in something called Plücker coordinates, after Julius Plücker, a 19th century German mathematician, which described the screw. And that the actuation of a single joint in the robot poses an instantaneous screw on a downstream link. And that notion is due to Sir Robert Ball, a British mathematician around the turn of the early 20th century, who was actually an astronomer who was trying to represent celestial bodies, or this was in advance of control of spacecraft. So the screw theory says that like the robot hand has an instantaneous screw, it has 3 degrees of freedom in velocity and 3 degrees of freedom in orientation change, described as a rate of rotation about an instantaneous axis direction. Now, I know this gets very abstract, and I hope this works with your audience. I'm not speaking down to your audience, but your audience might be people in STEM disciplines, chemistry or something outside this narrow field of mathematical geometry. Well, it turns out that the screw theory is the small signal model of electric circuits, but applied to mechanisms. Because what's very nonlinear in terms of determining the operating point, which you determine by gosh and by golly in your beginning electronics class, but the deviations, the small signal changes from the operating point, which is of interest in designing amplifiers, is the local linearization, and you use the techniques from your linear circuits class. The linearization of the machine mechanism, the operating point is the pose or the posture of the robot, giving a translational and an orientational positioning of the robot hand. The small signal analysis is the screw theory, which it's linear, and electrical engineers like linear mathematics, and I embraced that as a way of understanding robotic mechanisms, and that's been foundational. The research I've been doing since about 2009. The other thing is that in connection with speech, I've been working signal processing, digital signal processing, and teaching digital signal processing. And it turns out that if you want to do instead of just the position and then the linearization, if you want to do higher order series terms to more accurately describe a robot motion, you can combine series terms by a process similar to what's done in digital signal processing, of combining a signal with a impulse response, which is a characterization of a digital filter or a digital system. And that I combined the use of the screw theory to calculate derivatives, rates of change of motion. And by adding the digital signal processing idea, I'm taking the derivatives of the rates of motion to arbitrary number of degrees. That the state of the art in the field was people were taking higher derivatives, but with very clumsy techniques. And so I have 3 patents on this, which are assigned to WARF. So they're through the Research Foundation. They're essentially assigned to the university on combining the small signal analysis from electrical engineering, combining a mathematical trick for solving for higher order power series of nonlinear systems, and the screw theory from engineering mechanics to do the small signal analysis. So that's been the focus of my work since 2009. I mean, I've published some papers in collaboration with other people and continuing my work on speech science, but this is largely the focus of my research right now.
Yeah. Um, as one last thing I wanted to mention was last time we talked, you mentioned you got to meet Richard Feynman.
Yeah. Um, well, I hope your viewers are familiar with him. Is that, you know, I'm age 67, and so I go back in history a longer time than you or many of your compatriots. That I was at Caltech, and I think the year was 1978 when I was awarded my master's degree. And the circumstances were that I had spent one quarter. Caltech, where I got my graduate degree, and Northwestern, where I completed my undergraduate degree, are both quarter system. So there's 3 quarters in the academic year. Well, the fourth quarter is the summer session, I suppose. Uh, all my teaching has been on a semester here at the University of Wisconsin-Madison, and all my uh, own taking classes is on the quarter system. So I spent one quarter transferred from Northwestern University to Caltech. I was sort of ambitious. Well, I need to go to a fancier school or something. And I didn't have a happy experience at Caltech. It was sort of uh, I don't know if I was too earnest or didn't fit in with the culture of the student body there. So they gladly took me back at Northwestern University, and I was living at home, my parents and my brother, and I completed my degree. And so I received the the system they had at Caltech is that you were supposed to get your master's degree, and that if you didn't qualify to go on, you're supposed to do it. It was a coursework, a master's degree, equivalent of like taking 5 3-credit courses a semester. It was like 5 3-credit courses each. So it was a very rigorous load. And the idea is they would give you a master's degree if they didn't want to keep you on for the PhD. But if you pass your quals, you could go on for a PhD, which I was able to do. So I attended my master's degree graduation, and my parents didn't come out for it, and that was okay. It was sort of understood. Who came out for it? It's kind of a long story. One of my hobby interests I'm no longer active in it in my old age, is in ice dance figure skating. So one of my ice dance partners attended, and her husband was pretty noteworthy. She was a software, like a computer programmer at, I forgot which company. There was Burroughs, but her husband was an orbit trajectory designer, and a research engineer and a scientist at Jet Propulsion Laboratory. So anyway, I attended this graduation, and the speaker was Max Delbruck. And usually you expect somebody from the outside, some very famous celebrity. And here is this physics guy who did a late career change into biotechnology. And when you're kind of young and inexperienced, you don't know who these people are. Well, Max Delbruck figured out the thing about bacteriophages, which are these viruses which infect only bacteria, which might be a route to otherwise incurable, where antibiotics can't treat a bacterial infection. Well, anyway, he was offering us encouragement and explaining the Caltech way and everything. And so when this ceremony is over with, Richard Feynman was in attendance, and he was very recognizable, even though I didn't have social interaction. He made a beeline for me, thrust out his hand, shook my hand, and said, "Congratulations." And I asked my mom about, my mom from a part of from the Near East, where everybody has some conspiracy theory of it. He says, "Well, maybe he knew more about you than you knew what was going on. That maybe the fact that you left Caltech as an undergraduate because of some unhappiness, that maybe he felt that he was very happy for you that you returned as a graduate student and successfully completed a degree here, both for yourself as well as the reputation in the institution." Or maybe he just felt like it. Maybe he thought I was fresh-faced graduate student receiving a degree, and he just came right up to me, shook my hand, "Congratulations."
But yeah, um, so that's the time we have for today then. Thank you for meeting with me.
Well, I hope this is of interest to your podcast viewers, and thank you very much for having me as a guest.